So hello everyone, this is lecture 25 for the classical physics. In the last lecture we were discussing about the generalized force. Then we discussed about the non-conservative and conservative forces. And we discussed that how we define the force, means in the conservative system and non-conservative system, how we define the Lagrangian. In today's lecture we will see, means in the last lecture we have also seen the conservative forces where potential is depending on the velocity also. So this was the case in the EM field. So that's why we have to discuss Gauss transformation here. So it's a topic of electromagnetic theory. So you can see my lecture on the electromagnetic theory. There I discuss this in detail. Here I will take only those things which is important. Okay. So which we need here. So this Gauss transformation is something like Lorentz transformation in the space-time curve. So it's in the electromagnetic theory. So the effect of Gauss transformation of EM potentials on the Lagrangian. So we will see what will be the effect of Gauss transformation in the Lagrangian. So it happens in the EM field. So what happens in the Gauss transformation? This is our vector potential we know. So when we transform this, then A prime will be A plus delta F, del F. This F is nothing but a function of position and time. And this scalar potential will turn out to be phi minus del F by delta T. So just you need to remember these two potentials. This is scalar potential, this is vector potential. And they will go and undergo in the Gauss transformation will give you this value. Okay. And F is function of position and time. So this is the transformation, and E and B remain same in the Gauss transformation. Okay, so E prime will be E, B prime will be B. So you just need to remember these results, not more. Now from EM electromagnetic course we know E and B does not change under the Gauss transformation. So I already told you this. So as E and B are not changing, so Newton's equation of motion, we know this equation from the Lagrange force. You remember QE plus QV cross B. So this will remain change, means this will remain unchanged under the Gauss transformation. So just remember these results. So now main point is we know what is Lagrangian in the EM field. I already told you this expression. Half mv square kinetic energy minus, if we take the common, it will give you q phi minus q v dot a. So this is scalar potential and vector potential. So total potentiality will be given by this expression. So this is Lagrangian in for a charge in the EM field. Now we'll see if we take a Gauss transformation, then how this Lagrangian will change. So that is the point we are trying to solve here. So after Gauss transformation, L prime will be half mv square minus q phi prime plus q v dot a prime. So this will be your Lagrangian after the transformation. And now let's substitute the value of phi prime and a prime from here. Phi prime will be this, a prime will be this. So after substituting phi prime will be phi minus del F by delta D, and a prime will be a plus delta F. Now take these terms, half mv square minus q phi, and take this term q v dot a here. Then we take this term minus plus q del F by delta D here, and q del F will be here. Q v dot del F will be here. So these are your terms, all terms. Now see, this is nothing but same as this Lagrangian before Gauss transformation. So we'll write it as L. So L prime will be L plus this thing. So that's how our Lagrangian will undergo in the Gauss transformation change. So L prime will be L plus q del F by delta D plus q v dot del F. Now see, this is nothing but let's solve something. Means F is function of x, y, z and t, and this is position and time. So if you need to find the complete derivative of this with respect to time, so df by dt will be given by del F by delta x and delta x by delta t. That's how del F by delta y and del y over delta t. So del x over x will give you del x over delta t will give you vx, and delta y over delta t will give you this vy, and same del z over delta t will give you vz. So this is the expression you know from the derivative or the partial derivative results. So df by dt complete derivative given by this form when f is function of x, y, z and t. So in the last you will get del F by delta t and delta t over delta t. So that's why it will be 1. So you will get this result. Now from here you can see that delta over delta x will be differentiating this term. So it's like a dot product of del dot v, and this function is scalar. So del F dot v can be written in this form plus del F by delta t. So you know how we write this term. Dot product will give you vx, vy, vz, and here you will get del F by del x, x cap, and vx, then it will give you del F by del x vx. So that's how you can write these three terms in this form, and del F by delta t as it is. Now see this, if you take q common from here, this was the expression for the Lagrangian in the Gauss transformation. If you take q common, it will give you del f by delta t plus v dot del f. So this will give you the same expression. So q, after taking q common, you will get this expression as this. So it will give you q df by dt. So L prime will be L plus q df by dt. And if you take this q inside, then L prime is nothing but L plus dy dt and qf. So this will be your Lagrangian after the Gauss transformation. So that's how our Lagrangian will be modified in the Gauss transformation. Remember this. Under Gauss transformation, L of a charged particle moving through EM field changes by the total time derivative of function of position coordinates and time. So that's how our Lagrangian change, means total derivative of position coordinates and time coordinates with respect to time. Okay, so this is function of position coordinate and time with respect, and derivative of this with respect to time. So will give you your change in the Lagrangian. Now this was the result in the change in the Lagrangian. Now we'll see what will be the change in the Lagrangian equation of motion. So let's see effect of Gauss transformation on the Lagrangian equation of motion. So L prime is nothing but L plus df by dt. So we proved this. We written this qf as capital F, x, y, z and t. So this is function of position and time. So L prime is L plus this. Now Lagrangian equation of motion is nothing but d by dt of del L prime by del qj dot minus del L prime by del qj. So you know this result. Now in place of L prime we will write this term. So we will get this thing L plus this. So d by dt del L by qj prime, and this plus term I will write here d by dt of this. This can be written as f dot. So it will be d by dt of del f dot divided by del qj dot. Now this second term will give us minus del L prime. So minus del L by del qj, and then it will give us minus del f dot by del qj. So these four terms you will get after substituting this value in place of L prime. Now see, this is our old Lagrangian. This is our old Lagrangian, means we know this, and from there we know this result that this is equal to 0. Now we need to solve this to check if what the result we will get for this L prime. Okay, so let's see this f dot. So first, f is function of q1, q2 and t. So df can be written as del f by del q1 dq1 plus del f by del q2 dq2, and in the last it is function of time also. So del f by delta t dt. So that's how you will write it. Now we need to find f dot. So it means df by dt. Now divide by dt, you will get dt here, it will give you q1 dot, here it will give you q2 dot, and here it will give you del f by delta t only. So your f dot will be del f by del qj dot. Okay, because this will be your q1 dot, here it will be q2 dot, and here it is 2, then it will be q2 dot. So j dot, and this is f only. So del f over del qj dot plus del f by delta t. In the last it will give you 1 here, del dt by dt. So del f by delta t. So you will get f dot as this. Now you have f dot, and what you need here, del f dot divided by del qj dot. So when you take the derivative of del f dot with respect to qj dot, it will give you only, this will become 0, and this is qj dot term. So it will give you del f by del qj only. So del f dot divided by del qj dot will be del f by del qj only. So this will be your result. Now if you write del f by del qj in this, then what happened? Now it is equal to this, we already proved this. Now take this del qj this side and dt this side. So you will get this form. Now df by dt is nothing but f dot. So it will give you del f dot divided by del q. Now see this result. You can write this in place of this. So when you write del f dot divided by del qj here, and second term is also del f dot by del qj, so they will cancel out each other and they will be 0, and this was already 0. So see, you will get again the same result for L prime also, dy dt del L prime divided by del qj dot minus del L by del qj. This will also be 0. So what is the meaning of this? Means even after the Gauss transformation, the Lagrangian, the modified Lagrangian also satisfy the equation of motion for the Lagrangian. Okay, so these are the results. Under Gauss transformation, Lagrangian equation of motion doesn't change. So we already see this. Now if L is Lagrangian for a system, then it will satisfy Lagrangian equation of motion. Lagrangian will be modified under Gauss transformation. We already see how it will modify, and this modified L, that L prime, will also satisfy the Lagrangian equation of motion. So we already proved this result. Now we will see some questions. A classical system have following this. So this was given equation. This was action, s equal to this, dt. So this will be your Lagrangian. Then where q is generalized coordinate, so these are generalized coordinates, alpha and beta are constant. So which statement is true about the dynamics of the system? So option Y, dynamic is independent of alpha and beta, dynamic is depends on alpha, dynamic depend on beta, and dynamic depend on alpha by beta ratio. So we need to choose option. So how you find the dynamic of a system? First you need to find the equation of motion for the system. So how you can find the equation of motion? The Lagrangian is given, so you can find the equation of motion. So Lagrangian is this. You will find again del L by del Q dot. You will get this result. Then dy dt of del L by del Q dot will give you this result. Now this will be subtracted from this, will give you equation of motion. So after subtracting you will get only 2q double dot. Other terms will be cancel out. Okay, means this is del L by del Q and this is this. So subtract this from this. So you will get this will subtract this will subtract this, then you will get 2q double dot equal to 0. Then from here q double dot equal to 0, and that means q dot is equal to constant, only then q double dot will be 0. So it is nothing but dq by dt, so it will give you c1t plus c2. So q equal to c1t plus c2. So this will be equation of motion, and it is independent of alpha and beta. So dynamics will be independent of alpha and beta. Now let's see some more questions. So a particle is moving under the action of a generalized potential. So potential is given in the generalized coordinates q and q dot, 1 plus q dot divided by q square, the magnitude of the generalized forces. So we need to find the magnitude for generalized force. So we know from the previous result we proved for the generalized force the expression is this, minus del v over del q, where v is potential, plus d by dt of potential divided by del q dot. So here potential is depending on velocity also, so we'll take this component also. So just now put this v here and solve this expression. So just a simple differentiation and you will get this result 2 by q cube. Now there is one more question you will try. It's just same as question number 1. If potential u is given this in this form, 1 upon r, 1 plus r dot square by c square, then generalized forces. So use the same expression, this one, and you will get this result 1 upon rc square 2r double dot minus r dot square divided by r plus half 1 upon r square. So try this question and find the result this. So it will be a good practice. Now let's see one more question. A bead slides on a wire in the shape of a cycloid described by the equation yx equal to a theta minus sin theta, a 1 plus cos theta. So a bead is sliding, means this kind of cycloid is here. So equation is given, the question we have given x and y component changing only depending on the theta. So only one variable is there, or one generalized coordinate we need, that is theta, and this will be your cycloid. So x will change like this and y will change like this, where theta will go from 0 to 2 pi. And we need to find the equation of motion for the bead. Neglect friction between the bead and the wire. So this is our wire and in the form of cycloid, and bead will go like this motion, and x and y are changing with this form, x equal to a theta minus sin theta, y equal to a 1 plus cos theta. We need to find the equation of motion for this, so it will depend on theta. So let's find the Lagrangian first. So from here x dot will be a theta dot minus cos theta theta dot, so it will give you a theta dot 1 minus cos theta. Y dot will be minus a sin theta theta dot. Now for Lagrangian you need velocity, so it is x dot square plus y dot square half m. So from here you will get these things, and minus this is potential energy is given by this height, so it is mgy. So y is nothing but this a1 plus cos theta. So we will substitute these values in place of x dot y dot, you will substitute these values, and after solving this you will get this form. Now you have Lagrangian, this is your Lagrangian. Now it is depending on theta only, so you will find the Lagrangian equation of motion, so that is del L by del theta dot will give you this. Now take d by dt of this, will give you this expression 2ma square theta double dot 1 minus cos theta 2ma square sin theta theta dot square. Now find the del L by del theta. From the same Lagrangian you will get this form, ma square sin theta theta dot square plus mj cos sin theta. Now subtract this one from this one, you will get your Lagrangian equation of motion. So this will be your answer. Now let's take one more question. A block of mass m is suspended vertically from the ceiling by a spring of spring constant k. A pendulum of mass m is attached to the bottom of this block by a massless rod of length L as shown in the figure. So figure is this. So this is your ceiling and this is your spring with constant k, and this mass block is suspended, and now with this mass a massless rod is suspended, this m mass, and this is going in this motion, pendulum. massless rod of length as shown in the figure. Assume that the block can move only vertically and that the motion of the pendulum takes place in the fixed vertical plane. What will be the Lagrangian of the system in a suitable generalized coordinate? So we need to find a Lagrangian for this kind of system. What is happening here? This spring can move only in this z direction, not z. This was given in the figure. This is x direction, this is y direction. So this was given in the figure, okay, or the question. So this is moving in only in one direction, that is y, and this mass is here. Now this second system or pendulum can move in this vertical plane only, xy plane. So we need to find the Lagrangian for this kind of system. So for this mass or this particle, we have only one generalized coordinate, that is this y. So let's call the coordinate as y1, and for this we have two coordinates, so x2, y2. Let's call for them x2, y2. Now see, first write the equation for this, means Lagrangian will be kinetic energy of both and minus potential energy of both. So kinetic energy for this will be half m y1 dot square plus, now for this it will be x2 dot plus y2 dot square minus, now potential energy of both. So first see, this is moving in this side, means when this mass you suspend, it will go downward. So let's say it will go y1 distance downward, then potential energy will be let's say this is your equilibrium position, so it is in the negative of the gravity, so potential energy will be negative minus mg y1 because of gravity. Now there is one more potential energy, that is due to this spring constant, so that is nothing but k y1 squared divided by 2, that is displacement. So this is potential energy of this mass. Now potential energy of this will be nothing but this distance from the equilibrium position. So this is nothing but, means from the equilibrium position it will be y2, so we'll call it minus mg y2. Okay, so this is kinetic energy minus potential energy, this will be your Lagrangian. Now still we have all the variables. Now we need to simplify them or eliminate some of the variables. So how can we remove them? So for that we need to find some things, means we need to find this distance first. For this particle, what will be this x2? This x2 will be, if length is given, then this will be L sine theta. So this L sine theta will be this x coordinate, so x2 will be L sine theta. Now for this y coordinate, see it is displaced to this, up to this point, y1, then it will be y1 plus something. Now this is at this point, so L cos theta will give you this distance plus y1. So y1 plus L cos theta will give you y2. Now in place of x2, y2, you will substitute them, and in place of x2, y2 dot, you will find x2 dot from here, it will give you L cos theta theta dot, and y2 dot will give you L minus L sin theta theta dot plus y1 dot. So after solving them, you will just substitute the values and you will get this expression, half m y1 dot square. So it's just a simplified version of that, and after this it will go on, and this series start from here and from here, okay, and up to here. Then again we will take some terms which will be common from here, half m y1 dot square here and here, then m plus m will give you this form. So this is just a simple simplification, and you can solve this and you will get this result, and this will be your answer, okay, the Lagrangian. Now let's take the last question for today. The fulcrum of a simple pendulum consisting of a particle of mass m is attached to the support by a massless string of length L, oscillates vertically as zt equal to a sin omega t, where omega is constant and the pendulum moves in a vertical plane, and theta t denotes the angular position with respect to the z axis. If L d square theta by dt square plus sin theta g minus ft equal to 0, if this is equal to 0, where g is the acceleration due to gravity, describe the equation of motion of the mass, then ft is, we need to find the value of this ft. So this is equation of motion. So first we will use this all information to find the equation of motion, then we will compare that equation with this and find the value of ft. So let's see. This question is like this. This is your zt, and this rod is moving up and down in the vertical direction, in the vertical plane. It is moving like this, okay, and this is a massless rod attached with this m mass, and this is oscillating, okay. So we need to find the Lagrangian or the equation of motion for this kind of system. So how can we solve this? So z with time is changing as a sin omega t, so it is going like this, up and down, okay. So we'll take this as the equilibrium position. Now any potential energy in this direction will be negative, and this is your positive z direction to the side. So from here x will be L sin theta. So let's take any take any particular instant when this rod is at somewhere here, okay, and this was your equilibrium position, and this mass will be somewhere here. So this is your y component and this is your x component, and x component will depend on theta, so x will be nothing but this L sine theta. But this y component, this will be measured from here, so from here to here it was L cos theta, but now this zt distance will be subtracted, then you will get z as, means this I am calling it was y, it is z actually because this is z direction. So this z component will be L cos theta minus this zt, so this will be your z component for the particle when it is moving at this instant. Now this rod is at this point, so this will be your from measured from here because this is equilibrium position. So your x will be this and z will be this. Now you will have x dot will be this because you need the x velocity and z velocity for this mass. You need to find the equation for this mass now. So z dot will be minus L sine theta dot minus a omega cos omega t from here. So you have x dot z dot, then Lagrangian will be half m square of x dot square by z dot square, means velocity square. So that will give you this means L square cos square theta dot square, and then square of this will give you L square sin square theta dot square. Then you will take common L square theta dot square will give you sin square theta plus cos square theta will be 1 here, and here it will be 2ab, so it is nothing but sin theta cos theta means this term plus this, okay, means these two terms will give you 1, then this a square omega square cos square omega t, then 2ab will give you this term. Now the potential energy, now this height is what, L cos theta minus zt, and zt is a sin omega t, so this is in the negative direction, so potential energy minus mg, and this height, so this height is L cos theta minus a sin omega t, so minus mgh, and negative sign, this is because t minus v, and this negative is because of negative axis of the potential energy, this is plus and this will be your minus. Now you have Lagrangian, you can find the Lagrangian equation of motion by solving this, because all the terms are depending on theta, so you will find a Lagrangian with respect to theta. So del L by del theta dot will give you this expression, ml square theta dot plus ml a omega sin theta cos omega t. dy dt of del L by del theta dot will give you ml square theta double dot ml a omega cos omega t theta dot minus ml a omega square sin theta sin omega t. Now you will find the del L by del theta. So del L by del theta will be this minus la omega cos omega t theta dot minus mgl sin theta. Now subtract the terms. After subtracting that one from this one, in place of theta double dot we will write d square theta by d theta square. Wherever you will get theta double dot you will write this and you will get this expression. Now you can take the sin theta common and inside you will get this g minus this and equal to 0. Why we did this? Because we need this kind of function, ld square theta by dt square plus sin theta g minus ft equal to 0. So we made this in this form. Now we can compare this with that, and ft will be this a omega square sin omega t. So this will be your answer for ft. So that's it for today. In the next lecture we will see some more questions, and then we will see the Hamiltonian. So okay, thank you everyone.